Hi, this lecture is for worksheet 37, Electrochemistry, page 4. Last time we talked about reaction potential at non-standard conditions and the Nernst equation. Shown here is the Nernst equation at any temperature where E0 is the standard reaction potential at standard state. R is the gas constant in unit of joule per mole per Kelvin. T is the temperature in Kelvin. N is the number of electron transfer in the redox reaction. F is the Faraday constant in unit of joule per mole per volt. And Q is the reaction quotient. For a reaction at 25 degrees Celsius, you can modify the Nernst equation by combining all of the constant and also temperature at 25 degrees Celsius, and you will obtain the new Nernst equation as the following. Example 2F asks to calculate the non-standard reaction potential at 25 degrees Celsius. We will use the Nernst equation at 25 degrees Celsius. We know the value of standard reaction potential from problem 2E, which is 0.62 volts, and we know the value of N from problem 2D, which is 6 electrons. The only term we don't know is the reaction quotient. So our first step is find out the value of reaction quotient. The reaction quotient Q can be expressed by the concentration of product over the reactant. The exponents can be determined from the coefficient in the balanced chemical equation. Water and copper are not included in Q expression because they are in liquid and solid state. The concentration of all species are given. If you plug in all the value, you should obtain the Q value of 3.6 times 10 to negative 15. Now it's time to find the reaction potential. We will use the Nernst equation at 25 degrees Celsius. Plug in all the known values. You should obtain reaction potential at 0.76 volts. The reason why the non-standard reaction potential is greater than the standard reaction potential is because at this point, we start with very high concentration of the reactants. According to Lecture37 principle, high concentration of the reactant causes the reaction to shift in the forward direction, which means that it strongly occurs in the forward direction, or afterward it's very spontaneous or more spontaneous in the forward direction, resulting in a greater reaction potential. Example 2G asks, what would happen to the reaction potential at basic pH solution? Before we can answer this question, we need to understand the Lecture37 principle first. This principle states that when a chemical reaction at equilibrium is disturbed, the system responds to minimize the disturbance to reach a new equilibrium. For example, if you have a process A convert to B, and this process is at equilibrium, when either A or B is disturbed, the reaction will shift in order to establish the new equilibrium. Now let's take a look at example 2G. A basic pH solution contains high concentration of hydroxide ions. Hydroxide ions will react with available protons in the chemical reaction to form water. This is a neutralization reaction. Hydroxide ions will disturb the equilibrium by removing proton, causing the reaction to shift reverse toward the reactant to establish the new equilibrium. Because the hydroxide ion causes the reaction to shift reverse, which means that it's less spontaneous in the forward direction, this would result in a smaller reaction potential. Example 2H asks, what is the value of reaction potential when the reaction reaches equilibrium? First, we need to understand that the equilibrium position can be found at the minimum potential energy. Whether you start with a high concentration of reactant or high concentration of product, the reaction will shift until it reaches the equilibrium point. At equilibrium, neither forward nor reverse direction is favored, and at this point, the reaction potential is always equal to 0 volt. Example 2I asks, if Q less than K, will the value of reaction potential be greater or less than the standard reaction potential? When Q less than K, it indicates that this is not at equilibrium point. There are more reactants than product. Thus, the reaction will shift to the right toward product. This means that it is more spontaneous in the forward direction. This results in a greater value of reaction potential than the standard reaction potential. Vice versa, when Q is greater than K, this is not at equilibrium. There are more products than reactants. Thus, the reaction would shift to the left toward the reactant, which means it's more spontaneous in the reverse direction. This results in a smaller reaction potential than the standard reaction potential.